This video shows how to work on bigger matrices using both Gaussian and Gauss-Jordan methods to find values of 4 variables. Welcome to Numerical Solutions 2C Problems. We are to solve the system of 4 linear equations with variables x, y, z, and w using Gaussian elimination, both partial and complete pivot method, Gauss-Jordan elimination, then the iterative methods. Although a matrix is not necessary for iterative methods, let's convert the system to an augmented matrix for Gaussian and Gauss-Jordan elimination. Start with Gaussian elimination through partial pivoting. In this method, the matrix should be converted into a triangular form, where commonly we zero out those elements below the main diagonal. In this method too, we look for the pivot element, ideally valued as 1. So starting in column 1, interchange rows 1 and 3 to position the pivot element 1. Afterwards, we can then zero out the other elements in column 1. Start zeroing out element 2, 1 using 5 times row 1 less row 2 as the new row 2. The first element is computed as 5 times 1 minus 5 to have 0. The next element is then 5 times negative 1 minus 2 to get negative 7. Next has 5 times 2 minus negative 1 and get 11. Then there is 5 times negative 4 minus 2 to get negative 22. And last is 5 times 8.8 minus negative 10 to get 54. Since the first element below A11 is already zeroed out, continue eliminating element 31 with the equation twice of row 1 minus row 3 as the new row 3. First, there is twice of row 1 minus 2 to get 0. Then next is 2 times negative 1 minus 3 giving negative 5. Next is 2 times 2 minus 1 as 3. Then 2 times negative 4 minus negative 2 to have negative 6. The last element is twice of 8.8 minus 5.5 giving 12.1. Note as well that row 4 has 0 element in column 1. So after the two operations, we have already transformed column 1 in the matrix. With the updated matrix, we work on column 2 by finding a pivot element first. Take row 2 and divide it by negative 7 to have a new row 2. With the value of 1 as pivot element, it is easier to zero out the other elements in the column. Now we take out element 3 too by using 5 times row 2 plus row 3 as the new row 3. First is 5 times 0 plus 0 to get 0. Then 5 times 1 plus negative 5 is also 0. The third element has 5 times negative 11 over 7 plus 3, which results to negative 34 over 7. Next is 5 times 22 over 7 plus negative 6, giving 68 over 7. Then last is 5 times negative 54 over 7 plus 12.1, which is equal to negative 1853 all over 70. With the updated matrix, We can now proceed to zeroing out element 4, 2 with the equation 4 times row 2 minus row 4 as the new row 4. The first element is computed as 4 times 0 minus 0 to give 0. Next is 4 times 1 minus 4, giving 0. Then 4 times negative 11 over 7 minus 3 to have negative 65 over 7. The fourth element is computed as 4 times 22 over 7 minus negative 2 to get 102 over 7. The last element is 4 times negative 55 over 7 minus 13.15 to get negative 6,161 over 140. After the operation, the matrix will look like this. So checking on the main diagonal, the only element left for us to zero out is that in row 4, column 3. Completing column 2 of the matrix, we move to find the pivot element for column 3 and have it with the operation negative 7 over 34 of row 3 as the new row 3. Continue with eliminating element 4, 3 with the operation 65 over 7 of row 3 plus row 4 as the new row 4. Start with 65 over 7 of 0 plus another 0 to have 0. Then 65 over 7 of 0 plus 0 to have 0 again. The third element is computed as 65 over 7 times 1 plus negative 65 over 7, zeroing out element 4, 3. Next is 65 over 7 of negative 2 plus 102 over 7, resulting to negative 4. The last element has 65 over 7 times 109 over 20 plus negative 6,161 over 140, which becomes 33/5. Now that we have transformed an upper triangular matrix, we work on the variables values. Remember that each column has a specific variable designation. To solve them, we use back substitution, where we start from the bottom at row 4, where we get negative 4w as equal to 33/5, giving w as negative 33 over 20, or negative 1.65. The next is from row 3, giving z minus 2w as equal to 109 over 20. Plug in the value of w to have z minus twice of negative 33 over 20 as equal to 109 over 20, where z is computed as 43 over 20 or 2.15. Moving up again to row 2, the row shows y minus 11 over 7z plus 22 over 7w as equal to negative 54 over 7. By placing the values of z as 43 over 20 and w as negative 33 over 20, we get y as equal to 17 over 20 or 0.85. Then at the top row, the equation is x minus y plus 2z minus 4w is equal to 8.8. Place the solved variables again and get x minus 17 over 20 plus twice of 43 over 20 minus 4 times negative 33 over 20 as equal to 8.8, where x is computed as negative 5/4 or negative 1.25. Before showing a solution using complete pivoting, let's continue with the matrix with Gauss-Jordan elimination. As we had the upper triangular matrix from Gaussian elimination, we then zero out the last non-diagonal element in column 2, using the second row as pivot row with the operation row 2 plus row 1 as the new row 1. The first element is solved as 0 plus 1 as equal to 1. Next, we have 1 plus negative 1, making 0. The third element is negative 11 over 7 plus 2 to get 3/7. Next, we have 22 over 7 plus negative 4, which makes negative 6/7. And last is negative 54 over 7 plus 8.8 to get 38 over 35. So after clearing columns 1 and 2, this is the transformed matrix, where we are going to use row 3 as the pivot row to clear out column 3. That is for elements 2, 3 and 1, 3. So with the matrix, we work on the third column using row 3 as pivot row. First, we take out element 2, 3 with 11 over 7 of the third row plus the second row as the new row 2. First element has 11 over 7 of 0 plus 0 to give 0. Next is 11 over 7 times 0 plus 1 to have 1. Then 11 over 7 times 1 plus negative 11 all over 7 to give 0. The fourth element has 11 over 7 times negative 2 plus 22 over 7 to give 0 again. Then 11 over 7 of 109 upon 20 plus negative 54 over 7 to have 17/20 or 0.85. The matrix is then transformed as the one shown, where we are to use row 3 to eliminate element 1, 3. With the operation row 1 minus 3/7 of row 3 as the new row 1. First is to take 1 minus 3/7 of 0 as 1. Then 0 minus 3/7 of 0 to have 0. The third element is 3/7 minus 3/7 of 1 as 0. Then negative 6/7 minus 3/7 of negative 2 to get 0 again. The constants elements have 38 over 35 minus 3/7 of 109 over 20, giving negative 5/4 or negative 1.25. So after this operation, we are ready to work on the fourth column, which is just to eliminate element 3, 4. Since we are going to start working on a new column, let's determine the pivot row first. That would be using row 4. Simplify this row by dividing it by negative 4 to have a pivot element valued at 1. So we zero out element 3, 4 through twice of row 4 plus the third row to have the new third row. First element is twice of 0 plus 0, giving 0. The second is the same 0. The third is twice of 0 plus 1, which is equal to 1. Then there is twice of 1 plus negative 2, giving out 0 again. The last element is from twice of negative 1.65 plus 5.45, resulting to 2.15. After this operation, the augmented matrix is now an identity matrix where the variables for each column is still in the order of x, y, z, and w. We can clearly identify x from the first row as negative 1.25. The second row shows y as 0.85. The third row is for z, which is equal to 2.15. And w is from the fourth row, which is seen as negative 1.65. The next method is complete pivoting, where we will be starting from the original system. So back at the very start, we need to identify the highest coefficient from the 4 by 4 matrix. From the options, we need to place 5 to element 1, 1 to make it the pivot element. Fortunately, 5 is already in the first column, so we only need to flip rows 1 and 2, and in this way, the orders of the variables x, y, z, and w are still intact. Next is to work on zeroing out the non-diagonal elements from column 1, starting with element 2, 1. We use the operation 2/5 of row 1 minus row 2 as the new row 2. The first element is computed as 2/5 of 5 plus negative 2 to get 0. Next is 2/5 of 2 minus 3, giving negative 11/5 or negative 2.2. The third is 2/5 of negative 1 minus 1, resulting to negative 7/5 or negative 1.4. Then 2/5 of 2 minus negative 2 is 14/5 or 2.8. The last element is solved as 2/5 of negative 10 minus 5.5, which becomes negative 19/2 or negative 9.5. With the updated matrix, we work on eliminating element 3, 1 with the fifth of row 1 minus row 3 as the new row 3. The row starts with a fifth of 5 minus 1 to have 0. Then a fifth of 2 minus negative 1 to get 7/5 or 1.4. Then a fifth of negative 1 minus 2 to have negative 11/5 or negative 2.2. Next is a fifth of 2 minus negative 4 to get 22/5 or that is 4.4. Then the last element has 1/5 of negative 10 minus 8.8 to have negative 54/5, which is also negative 10.8. So after fixing row 3, the newly transformed matrix looks like this, where all other elements under column 1 are zeroed out. Moving on to the second column. Identify the highest coefficient from the elements in the 3 by 3 matrix, in which the highest coefficient is 4.4 from element 3, 4. We need to place this element into 2, 2, so we swap column 2 with 4. And take note that by doing so, the variables y and w are also rearranged. Next is to bring 4.4 up to row 2, and that is through swapping rows 2 and 3. And since we had rows operation, the variables order stays the same as x, w, z, and y. With the pivot element as 4.4, zero out element 3, 2, with 2.8 over 4.4 of row 2 minus row 3 to have a new row 3. That is with 2.8 over 4.4 of 0 minus 0 to have 0. Then 2.8 over 4.4 of 4.4 minus 2.8 as also 0. And also 2.8 over 4.4 of negative 2.2 minus negative 1.4 as 0 again. Next is 2.8 over 4.4 of 1.4 minus negative 2.2, which equals to 34/11. Then 2.8 over 4.4 of negative 10.8 minus negative 9.5 as 289/110. With the new format of the matrix, we also use the second row to zero out element 4, 2. We do just that with 2 over 4.4 of row 2 plus the fourth row to be the new row 4. Start with 2 over 4.4 of 0 plus 0 to give 0. Next is 2 over 4.4 of 4.4 plus negative 2 making 0 again. The third element is 2 over 4.4 of negative 2.2 plus 3 as equal to 2. Then there is 2 over 4.4 of 1.4 plus 4 to get 51/11. Then the last is 2 over 4.4 of negative 10.8 plus 13.15 to have 1,813/220. Now note that the third row has most elements already zeroed out, so we just have to flip this as the new row 4 and check that we already have created an upper triangular matrix ready for back substitution. So the final matrix will be like the one shown, whereby the order of variables starts with x, then w, followed by z, and then y. With back substitution, start with the bottom row and get 34/11 of y as equal to 289 over 110. So y becomes 17/20 or 0.85. Row 3 has 2z plus 51 over 11y as equal to 1813 over 220. With y as 17 over 20, we get 2z plus 51 over 11 of 17/20, where 2z becomes 43 all over 10, which gives z as 43 over 20, or 2.15. The second row is translated as 4.4w minus 2.2z plus 1.4y as equal to negative 10.8. Place the previously solved values of z and y and simplify to have 4.4 as negative 7.26, where w becomes negative 33 over 20 or negative 1.65. Then from the top row, we have 5x plus 2w minus z plus 2y as negative 10. Also place the values of w, z, and y, then simplify to arrive at 5x as equal to negative 6.25, where x is taken as negative 5/4 or negative 1.25. Through iterative methods, the system can be solved after determining if it can actually be approximated. Work on the first column for the variable x. Upon observing 2x, 5x, and x, we pick the second equation for x, as it has the highest coefficient among the three. Now check the coefficient horizontally. Is the coefficient of x greater than or equal to the summation of the absolute values of y, z, and w? That would be 5 compared with 2, negative 1, and 2, where 5 is equal to 5, so x passed the check. Now check the coefficients of y, and 4 being the highest, we'll tell that the fourth equation is 4y. Check this horizontally. That's comparing with x plus z plus w, or that is 4 compared to 0 plus 3 plus 2. However, 4 is not greater than or equal to 5, so at this point, we cannot continue with the iterative methods.